So how many forces should you have drawn? 2 forces. There are 2 forces acting on the cake. Okay. So, what's one of the forces? Sorry, give us one of the forces acting on the cake. Okay, so 1 point's up. Okay. Once we draw it, we want to label it right away. Okay, so what would be, this is a force, so F. How should I label this particular force, the one that points up? Yes. Well, no, so we want to be more specific, right? Because we have to talk about what is the agent, what's making the force, and what is the object, Dana. Yeah, this should be the force of the table on cake. Okay. The more you do this, you could get to the point where you did just label this force 1, but while we're getting to that point, we want to have that full label. What is the agent? What is the object? Yes, Zara. So all forces require an interaction between something in the environment, in this case it would be the table, and then the name you gave to the object, which in this case we're calling cake because it is cake. I feel really funny just, yeah, cake, 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 cake. No, so the table is pushing up on the cake. If the table wasn't there, there would be no force pointed up. You can think of the question too, like what kind of force is this? Of the 2 kinds of forces we talked about on Friday, what kind would this be, Mariella? It would be a normal force, right? It's an example of well, what are the characteristics of a normal force? It requires contact, and its direction is always not necessarily up, but pushing, right? So if I instead ask the question, like, what is the normal force of the cake on the table, what direction would that be? Down, right? So normal forces are always a push, depends on how things are stacked. Okay, what is the other force we're going to want to draw here? Let's see. Charshal? It's pointed down. And how do you want to label it? Earth on cake. And again, let's refresh ourselves from Friday. What would be the category? What's the kind of force that is? What would it be, Aisha? It's a long range. What's like the name for it? Weight, or also gravity, right? And yes, a characteristic of weight and gravity is that it is long range. What would its magnitude be equal to? Let's just keep reviewing from Friday. What would the magnitude be, Mira?
The weight of the cake.
Which would be, how would I calculate that? No, okay, it looks like milligram, but it's actually, Tatiana? It looks like milligrams, but what is it actually? Mass times gravity. Yeah, and I know, and it's one of the things that gets very tricky, right? Sometimes a combination of letters will be a unit, sometimes it'll be a formula. Yes. Well, so usually, in writing, formulas are in italics and units are not italicized. So if you were doing that like handwritten, the formula should almost be, like, I can't write italicized, but like you would do it at a slant, whereas the units would be capitalized. It's another reason why sometimes it's good to write out the math, like the multiplication in between variables rather than it being implied, right? So that's another thing to kind of keep it separate. But it's a really good point. It's confusing. It definitely is. Okay. So that's we reviewed, we applied some of the concepts that we did on Friday. We need to pick back up. So basically what we did is we did kind of like steps 1, 2, and 3 of a free body diagram. And we're going to continue the process on how we would finish it. So we're going to go back to the example that we're working on Friday. Yeah.
Is the force of like Earth on the table greater than the force of the table on the cake? The table, like,
so yes, we'll go into the specifics of the physics behind gravity. Basically, the more important factor here is the mass of the objects. And yeah, the mass of the Earth is much, much larger than the mass of the table. But you're right, there's technically a third force here you could draw. That would be the gravity version, the weight of the table acting on the cake. But it's such a tiny force, it doesn't matter for the ones that we have on here. But you're right, there is technically a third force here. When we think about objects near the surface of the Earth, we're going to worry about weight, and weight is just what happens because of the Earth, not because of the other things. That's a good question. And in fact, if we can do the calculation in our next unit to see, I mean, it would be something like 10 to the 20th difference in size, like millions and millions of millions of times smaller. Well, which is why we're not gravitationally attracted to each other, like orbiting each other, because of just how much smaller those forces are. Any other questions about this? Okay, so we're going to go back. So this slide is where we left off. Okay. So this is the last place we had gotten to on Friday, where we said, here is Fiegel. Fiegel has two forces acting on him. We have the force of the elevator on Fiegel, pointed up, and we have the force of Earth pulling down on Fiegel. So I'm just going to give you a minute to kind of find that spot in your notes, and if you need to sort of recopy something down, you just need the diagram for right now. Okay, so I'll give you a minute with this slide. No, it can, right? So we can push on something with more. We'll look at an example after we finish this one. Okay. So again, we've got these two forces. We've got the force of the elevator pushing up on Fiegel and the force of the Earth pulling down on Fiegel. Now, if you think back to Newton's second law, which said the acceleration equals the net force divided by the mass, well, we can't use any old force to go in here. We have to figure out the net force. So what is it that we have to do with all of the forces acting on our object to figure out the net force? Got to add them up, right? We have to add them up to figure out what is the one force that is equal to the 2 or the 3 or the 55 or however many our pushes and pulls there are. We have to add them up until we get to just one force. And to help us do that, we're going to think about doing that in the x direction and think about doing that in the y direction. So step number 5 is to write Newton's second law in the two different directions, okay? And then we have to take the forces and put them into the two different categories. So if the force is in the same direction as the coordinate axis, make it positive. And if it's in the opposite direction, subtract it. And we'll do that on our next slide as like two separate examples, right? And by the end, every single one of your forces will either be added or subtracted, either in the x direction or the y direction. Kind of like a checklist. Oh, the force of the elevator is plus y. The force of the earth is minus y. And then once you've done all the forces, you can do the adding part. So before we move on to writing that out, make a prediction. Do you think we will be adding or subtracting the force of the elevator on Fiegel? And do you think will we add or subtract the force of the earth on Fiegel? So just write down your prediction in your notes. Okay. So I like to think about doing this as sort of like two different columns, right? I'll do a column where I'm thinking about what's happening in the x direction and a column about what's happening in the y direction. Okay. So this is just our drawing. Again, I just moved it to the middle, and I'm thinking about x and I'm thinking about y. What I've done is I've just sort of rewritten Newton's second law a little bit. So I'm putting the mass kind of like as a fraction out in front. Because what we're working on, the piece that we're working on is this. What do I get when I add up all of the forces in the x direction? I'll get a number, or it could be 0 or whatever, but I'll get something, and then I'll divide it by the mass, and I've got my acceleration. Likewise, you'll notice this piece has add up the forces in the y direction, and that'll tell you the y acceleration. Right? So if you think back to like our projectile motion, we had one acceleration in the vertical, but no acceleration in the horizontal. Right? They could be two separate numbers. Let's start off with the acceleration in the x direction, adding the forces. Remember this little symbol here, this little sum symbol just means add them all up. Add up all the forces in the x direction. What forces up there point along the x direction? What direction does force of Earth on Fiegel point? Remember, if it was to point in the x direction, it would point left or right. Do we have any forces pointed left or right? No. So if I add up nothing, what do I get? Nothing. So in the x direction, the sum of the forces is 0. What can you conclude about the acceleration if the sum of the forces is 0? What should A be equal to? It's not a trick question. 0, right? So right away, we got some information really quickly. We got that acceleration in the x direction equals 0. Remember, that has a special name. The object is in equilibrium. In which direction? In the x direction, okay? So we can say in the x direction, we can say the acceleration is 0. Why? Because the force is 0. And another way to communicate that is we're in equilibrium. All right, any questions about the x direction? This is definitely the easiest way it could come out, right? There are no forces. Adding nothing is really easy. It's just 0. Sorry. So Fiegel is the object, and we're describing how it is moving. And we're able to say that it is in equilibrium in the x direction. And we've talked a little bit about, well, that means it's either at rest in the x direction and stays at rest, or is moving at a constant velocity in the x direction, and that's not changing. From our analysis, we can't say which. We just know that whatever he's doing, it's not changing, but we don't know exactly what. But if you think back, like if you're riding an elevator, you're probably standing still. You're not walking back and forth in the elevator. So he's probably at rest. All right, so now we want to do in the y direction. Again, I need to look at each of my forces and decide, well, is it 0 because it's not pointed in that direction? Is it positive or is it negative? Which one do you want to start with? Jen, which force do you want to start with? Okay, so force of elevator on Fiegel, is that going to be positive, negative, or should we not add it at all and make it 0? Positive. Why positive? It is pointed in the same direction as positive y. So we will do plus F elevator on Fiegel. Okay. How about the force of Earth on Fiegel? Positive, negative, or 0? Negative. Gavin, how do you know it's negative? We want to be, that tells us half of it, because we also have to compare it to what we chose as our coordinate axes. Because I could take this whole situation and make positive y point down, and then we'd have to switch what was positive and what was negative. So it's both pieces. You have to, it's kind of like, remember for acceleration and velocity, are you speeding up or slowing down? And it was, are they in the same direction or in opposite directions? Similar idea here. So you have to look at both the original and your coordinate axes. But at the end of the day, we get that it should be minus force of Earth on Fiegel. Now, depending on what you might know about the question, maybe at this point you know the numbers. Maybe you know this number is 500 newtons, and you know this number is 300 newtons, and then you could just figure out the number. We're going to kind of analyze it to see, well, we can figure out this number because we know the mass of Fiegel, and we want to see how much, we can figure out this number because we know the mass of Fiegel. We want to figure out this number based off of that. But this is step 5, just adding up the forces. And this whole thing is, I would do this, right? I would do 1 divided by m, and that's equal to ay, right? So that's just that formula. Newton's second law, got the sum of the forces equal to the acceleration. Okay. Ay, yep. And we already know, we finished our analysis for ax. Ax is 0. So we're already halfway done. So then, yes, Layla. So this is a math symbol that means add things up, because there might be 1 force or 2 forces or 3 forces. It's just a shortcut to say add everything up. So it's the sigma is the name of the letter, and it means sum in this case. And then the way the reference table tells you that is they just say F net, force, the net force, and you have to remember that means you have to add everything. Net means sum. Exactly. So F net is equal to sum of the forces. Yeah, they're equal to each other. I like to write it this way because then I think it makes it clear that you need to add up everything. Sometimes people want to do net force and just pick one of the forces, and that's not the full story. Or they think it's just adding 2 forces, but it could be adding 3 or 4 or 5. I like the sum because it's like, just add everything up. All right, so step 6 is going to be, we've already sort of done step 6 a little bit for the x direction, but we're going to now apply it to the y direction. You have to kind of make a choice, and it depends on what the question gives you. Okay, so you're going to do a little bit of algebra to figure out your answer, but there are 2 different kinds of answers you might want. Sometimes you know that A is equal to 0, and you'll use that to figure out one of the forces. That's what we're going to do for this example. But of course, you could be told all of the forces and you're going to figure out what A is. Right? So again, it depends on the question, and we'll get some practice with that over the next few days. Sometimes you already know the acceleration, and sometimes you don't. Right? So again, sometimes you know A equals 0, and you're solving from one of the forces. Sometimes you're solving for A from the given forces. So for example, in the x direction, we knew A should be equal to 0 because there were no forces. So that's like an example of the first way. And now we're going to do it in another way where we were told information in the question about the acceleration. So let me pull up that question part from the slides on Friday. I forgot to put this. We'll get it here. All right, so the question told us that Fiegel is riding in an elevator that is moving at constant speed. Draw and analyze a Freebody diagram. So the question has already told us what the acceleration is equal to. What is the acceleration equal to?
0.
It's equal to 0. What part of the question tells you that? Moving at a constant speed. Okay, so we can come back to our question here. And now I can finish the analysis in the y direction. It said, again, AY equals 1 divided by the mass, F elevator on Fiegel, minus F Earth on Fiegel. Okay, so we're back at, that's what we had gotten to on step 5. And now we're going to use that new piece of information. Yeah, Shelly. Yep. Yep. So our sum was do plus force of elevator on Fiegel, subtract the force of Earth on Fiegel, and with that new piece of information from the question, the acceleration, the y direction is 0. All right. So what is this equal to? Also 0. And so let's see, I have the force of the elevator on Fiegel minus the force of Earth on Fiegel equals 0. So what is true about those two forces? Okay. Yeah, it's an equilibrium, but those two forces, I can say something about their magnitudes. They must be equal, right? That's the only way you can add these two things and get 0 if however long this arrow is equal to however long this arrow is. So I can say at this point that this force is equal to that force, and I've completed the analysis. So sort of the answer here is that the force of the elevator on Fiegel is equal to the force of gravity, but let's do it the other way, is equal to the force of Earth on Fiegel. So those two forces balance out. But it doesn't have to be that way, and you'll try an example where it's not. Okay. Any questions? Sarah?
What do you mean, like, okay, so when I get the part that is 0, what do you mean by, like, that is?
So I've got two different each individual force is not 0, right? How can I add two things and get 0 if the individual things aren't 0? Well, when you're talking about vectors, they must be equal in magnitude and opposite in direction. So we can already see from the drawing they're opposite in direction. But if let's say this force was 10 newtons and this force was only 5 newtons, would we get 0? No, and the net force, I saw Cheyenne motion it, the net force when I add 10 and 5 would be 5 newtons up. And again, don't think of that as like, oh, one force won. It's not about winning. It's just about what do you get when you add up the sum, right? Because let's say, okay, sure, maybe the Earth is pulling down with 5 newtons and the elevator is pushing it with 10, but maybe I tied a little, through a rope to Fiegel, and Fiegel is holding onto the rope, and I'm pulling down with 5 newtons. What would be the sum now? 10, 5, and 5, that would be 0, right? So that's why we want to think of it as like this net force. We have to do all of the forces that are going on. And that's a really interesting thing. Just because the sum of the forces is 0 doesn't mean all the individual forces are 0, right? It's not like, oh, the sum is 0, so that means there is no forces at all. It just means when you added them all up, you got 0. Yeah.
There's only 2 forces, though.
In this case, yes.
So that means that
Well, they're not each 0. They're some number.
Yeah, like when you add them,
Yeah.
they equal to 0.
Yes.
They have to be equal. But how can the force of the Earth and the force of the elevator be equal?
Sure. So because they're happening for different reasons, right? So the Earth on Fiegel is gravity, and that just has to do with the masses and the distance. The force, though, on Fiegel from the elevator, it's just enough force so that the total force is 0. Think about like leaning on a desk, right? If I lean on the desk lightly, that's a different amount of force than if I push up on the desk and support myself, right? But and thankfully these desks don't do that, if I tried to push too hard on the desks, what could happen? They could break, right? So the normal force is this weird force that it's like as much as it needs to be and nothing more, but if you try to make it too much, it gives up. The object will break. So normal force is kind of strange in that way. Remember, there's no formula that says this is the normal force. The normal force is what the normal force needs to be. And in this next question you're going to try, you'll see that. We're going to make it so that the acceleration of Fiegel is not 0 anymore. If the acceleration of Fiegel is not 0, the net force is not equal to 0. So that could mean the normal force is bigger. It could mean the normal force is smaller. Gravity, though, would stay the same. Unless you make Fiegel have more mass, the gravity will always be the same. It's his mass times 9.81. There's nothing I could do on the surface of the Earth to change that number. But the normal force, sure. And think about it. You're riding an elevator and the elevator starts to move upwards. You feel different than when the elevator starts to move down or when the elevator is going at a constant speed, right? So I hope that gets the idea. Like the normal force doesn't always have to be some particular number. It can change accordingly. In a lot of ways, that's like how a regular scale works that you step on. It's measuring how much normal force it takes to push you back up, right? And depending who steps on the scale, it'll say a different number because it can change the normal force that it needs to do. Sorry. Mm-hmm.
Are you talking about the net force?
So the net force we knew was 0. And the only way these could add together to give us 0 was if they were equal but in opposite directions. That's sort of the chain, right? You go, well, it's in equilibrium, so that means A is 0. Therefore, Newton's first law says add up all the forces, you should get 0.
So like the force that is needed to keep you on the earth is equal to the force that is needed for the elevator to move you up. Sort
of. That is the force the elevator needs to provide so you move at a constant velocity or remain at rest. So when you step on the elevator and nothing is moving, that is how much force the elevator needs to provide, right? And again, if you're interested in things like engineering and architecture, this is like when you're designing a building, you have to think to yourself, well, how many people could there be in this building? The floor has to be strong enough so that if it needs to provide 10 tons of force up to keep all the stuff supported, it's got 20 tons of capability, right? Because you don't want to be like on the edge. It's like one more person walks in and then your building collapses. So like it's kind of weird in that way because the normal force can be any amount. Okay. So what I want you to try now at your tables is it's a similar setup of the steps, but what you're going to do instead, hold on. What you're going to do instead is now the acceleration isn't going to be 0. What is the acceleration? Let's just do that part together. What is the acceleration? 2 meters per second. Oh, there's a typo. 2 meters per second squared. And in what direction? Up. Okay. So you're going to need to use that piece. So you don't have to start over. You can start from where our last line was, except instead of acceleration being 0, now it needs to be 2. But is it positive or negative? You have to think about that. And now that you know the mass of Fiegel, you can use that to figure out you can actually get a number now. So let's do like 4 minutes for this, and then we will talk about it. If you want to work on the whiteboards, you can. It's like in between. It's over here. So again, you do not have to do the whole analysis from the beginning. You can start with the last line that we have. Yes. Let's get the other whiteboard. There's 2 in between. There you go. Again, you do not have to start from scratch. You can use what we've done together, but now do this part about the acceleration not being equal to 0. Okay, we've already done the adding of the forces part. How do you use this new piece of information? How do we use this new piece of information? Good. A is not 0 anymore. How do you use that?
You know the math, you include that here?
Yes.
Okay, but then do you use AX or AY?
Why? Because we know in the x direction things are still 0. There's no new force in the x, so we don't have to worry about the x piece. It's because of how we drew it. We drew this together, so we said x is going left and right, and y is going up and down. You can just start at the equation part. Like, how could you figure out how much this needs to be? Is that who is here? What's up? 12 o'clock.
12.
Yeah. So we're starting at this point here, except now instead of AY being 0, it's 2. Right? What you're saying is now instead of AY being 0, now it is 2. How does that change what we're doing? So this should be 68 times 9.81. Weight is m times g. Well, you can, but then you kind of have to, like, the units aren't going to work out here.
Wait, how would I write it?
So the way I would write it is I would put the 68 kilograms there, right? And then when you did the multiplying,
Wait,
you
where?
could can't.
Like, where would you? What do you mean?
This should be 9.81 meters per second squared times 68.
Okay, and then where do I put this?
Well, this is what you're solving for, so that doesn't go anywhere there. That is what you're gonna exactly. That is the equal. About another minute here. I'm seeing good stuff. So AY is just that number 2 on the other side. So you have 2 equals a number minus this, and then all that side. So you move like 68 to the other side, right? And then you would add this over there.
Okay.
Right, so I'm seeing the equation set up correctly. Yes. So that puts kilograms there. And then we have a formula on how to calculate this number, how to figure out the weight of something, mass times gravity. Nope, so this part won't be 0 anymore. Because look, how could then 0 would equal 2? And that's not possible. Right. All right, so again, I'm seeing most tables have gotten to the formula. So let's all get on the same page there, and then we'll take a look at how to solve it. So the big thing is making sure you know whether the acceleration is, if it should be positive or negative. Why did you decide to make it positive? Because it's going up. Positive y goes up. That means it should be positive 2 meters per second squared. Then it's 1 over the mass, 68 kilograms. Okay. Then it is force of elevator on Fiegel. Then we have to do the subtract, right? Because if the force of elevator on Fiegel is positive and points up, then the force of the earth on Fiegel points down. Okay. Force of earth on Fiegel. And we know how to figure out this number. We get this number by doing 68 kilograms times 9.81 meters per second squared. Again, that's just, you put that in a calculator, you get some number. So let me solve this for, we need to solve for this. This is what we're trying to get the number of. So the first thing I would do is multiply each side by 68 kilograms. Right, I'm kind of thinking of it kind of like I'm cross multiplying. So I would have 68 kilograms times 2 meters per second squared equals F elevator on Fiegel minus, and then 68 kilograms times 9.81 meters per second squared. And then I would add this to the other side. I guess that's a weird music they're playing. So now it would be, so then I'm going to get some number that is bigger, right? Because I am now adding. And that's how the normal force can be bigger than the weight.
Get rid of the fraction. Didn't you already, like, you don't.
Right, but so what I'm saying is I still need the 68 here. If you don't have the 68 there, the units won't work. You see that?
But it's like you're multiplying it by 68 twice.
No, because when I cross multiply, I just, instead of dividing on this side, I'm multiplying on that side. That's the difference. Okay. You're welcome. So right. So how do I? Let's do. So it's 68 times 2. So this side is 136 newtons. Then if I do 68 times 9.81. Okay. And then I add this to the other side. So do 136 plus 667, and I get the force of the elevator on Fiegel is 803. So if I drew that, that would mean this force is longer than this force. And that's why, so what direction does the net force point? Up, right? Because, and I can even tell you by how much, the net force is this. So the net force would be 136 newtons up. You could also ask this question, what if instead of being positive, it was negative 2 meters per second squared? And then you would get a number here that was smaller, and the net force would point down, right? So that's kind of it's like this famous elevator question. And you can feel this when you ride the elevator. When the elevator starts accelerating upwards, you feel like, whoa, like you feel a little bit heavier because your feet are being pushed up towards you. The normal force is bigger than your weight. The flip side is when you start going down, you feel like, oh, like a little bit lighter. That's because the normal force is smaller than your weight, and you get that sense of weightlessness. Yeah. No, not 6th period.